Good afternoon, everyone, and thank you for attending today's webinar, Key Tips for Using and Operating Safety Networks, brought to you by Siemens and Design World Magazine. We would like to thank our presenters today, Tom Ellswick of Siemens and Cory Morton of B&R Automation, for being here. I'm Leslie Langnaw, Managing Editor at Design World Magazine, and I will be your moderator today. Before we get started with the presentation, just a few housekeeping details. If you wish to tweet about this, you can use hashtag DWWebinar anytime during or after the presentation, and we will have a Q&A session afterwards, but you can go ahead and enter your questions at any time during the presentation, and we will ask them once the presentations have finished. First up is going to be Tom Ellswick, who has more than 20 years automation experience and is part of the Factory Automation Product Marketing Group. Prior to joining this group in November of 2011, Tom was a principal systems engineer with responsibility for the factory automation safety integrated products. He has held positions as a software development engineer, project engineer, and project manager, as well as various sales and business development positions. Cory Morton has held several positions in his 4.5 years with B&R Industrial Automation. In his current role as a solutions architect, he works closely with the sales team reviewing customer application requirements and providing technical expertise on new and existing B&R technologies. Based on his close interaction with customers and their applications, he works with R&D at the global B&R headquarters in Egelsberg, Austria, to specify new technologies and functions to meet the needs of the North America market. And without further ado, I'm going to turn the microphone over to Tom.
Okay, thanks, Leslie. So in talking about international field bus and safety standards for factory automation, I guess I'll be talking about ProfiSafe today for a few minutes. And just before I do that, I wanted to comment on the standards landscape around safety buses in general. And so on the slide, on the right, down the right-hand side of the slide, you see the various standards related to safety. So ISO 13849 in the middle, 60204 for the U.S. and FPA 79 and others. And so those safety standards have evolved over the last 10 or 15 years quite extensively. And then on the left-hand side of the slide, you see other standards that aren't safety specific, but related to security and installation and various things. And so ProfiSafe, I'm highlighting the IEC 61784-3-3. ProfiSafe is actually spelled out in there as Profile 3. And so there's a lot of standards work out there, a lot of open standards, and so there's a lot of adoption both by the various vendors as well as by the people that are actually doing the applications in their facilities. And so ProfiSafe is history. It's a profile based on Profibus and Profinet. And so Profibus covers both factory and process automation and has been used extensively worldwide, has a huge installed base. And then Profinet is based on standard Ethernet. It's a complementary network. Basically, it's not something different. It's not additional hardware. It's just your normal Ethernet infrastructure with a protocol called Profinet. Well, ProfiSafe is a profile for both of those. In 1999, first specification for safety communication was established, and that was ProfiSafe. And ProfiSafe is involved to become the leading and most comprehensive safety communication technology in the world. So if you look at the amount of installed nodes, the industries, everything else, ProfiSafe is according to the studies we've seen, the #1. And of course, it's evaluated by the various certifying agencies like TÜV. Okay, so how does it work? The ProfiSafe protocol, safety messages are transmitted on existing standard bus cables in coexistence with standard messages. What that means is you can run your safety on a separate network, a separate Ethernet network, a separate Profibus network. That's perfectly allowed, and segment that from your standard control tasks. You don't have to. In general, some people do have networks where they put video and audio, as well as their control on a single network, and ProfiSafe will be perfectly happy with that as long as you have the bandwidth to support the speeds you need, no issues. Often people do segment out their control network, and in that case it's extremely common that people are running both their safety and their standard control communications on the same network. And the reason that we have total independence from the base transmission channels is over on the right-hand side there's a circle called black channel. And the concept, what that means is the channel, meaning the gray standard protocol down through the wire and back into the other device, that's not relevant to the protocol. And so the safety is actually done at the application layer. So you see ProfiSafe layer up at the top, and then the safety application. Whether, let's say that on the right it's a safety output module and on the left it's a safety CPU, the safety I/O module packages the ProfiSafe packet and does all of the checks that you see over on the left, safety measures that are included. It says there's things like consecutive numbering, there's time expectations, code name, all these things that happen at the protocol layer. The user never sees it, but they happen. All of those things get done at the application layer inside of the module, and we'll look at a safety module next. But that happens in the module, and at that point, whether it goes out on a copper network bus or wireless or fiber optic, or even on the backplane between a safety CPU and a safety I/O module in the same rack and a PLC, that's not relevant to the safety communication. Now, of course, the protocol has to be able to detect any errors that could occur, such as, let's say this is a wireless network and the wireless network browns out. Well, that's why things like the time expectation is in there. So the CPU on the other end would get the packet and realize, no, it's been too long since I communicated, or there's a checksum error, or the messages are coming in the wrong order. Basically, that's detected at the CPU layer. And so how does it work? It's handled by the safety CPUs and then the safety devices on the other end. And that's why Siemens puts a lot of stock, when I'll show you the applications right near the end here, we put a lot of stock in saying that, wireless safety is available, standard networks are available, fiber optics, and so forth. But it's just a ProfiSafe, it's an Ethernet packet or a Profibus packet that has all these extra checksums and so forth occurring at the underlying level, not manipulated by the user. And so this is an example of a safety output module. And the real thing I wanted to get across here is still on the how does it work. The right-hand side, you see these little pulses going around. So inside of the module, that's the dashed lines. Inside of the safety output module, there are two microprocessors and various other things happening, but the two microprocessors are there to do two things. One, on the right-hand side going out to the contactors, it's doing diagnostics functionality as well as, of course, controlling the output. And so those diagnostics functions, that establishes what safety level you actually can attain from your application. Are there two contactors? Are there one? Can we detect these kind of faults and those kind of faults? That's all one function that's being done by the module. The other thing is going the left side where you see the terms data and CRC over here on the left. That's the communications. That's actually the ProfiSafe that's going to go from here to the CPU. And so the CPU and the module, I talked in the last slide about the communications and the checksums and all the checks that are going on. There's actually two microprocessors at the module. And so if there are any issues with communications, if there's any issues with the data that's coming across, that's going to be detected, in this case, by the output module. And at that point, no matter what the CPU is doing, this output module is going to go to a safe state, which means it's going to turn off the outputs. Let's say you got well, we haven't communicated with the CPU recently, and we indicated we needed to talk to the CPU every 50 milliseconds in order to get the safe response time for the overall safety function. Well, this module will detect that at this level and turn off. The same thing happens with input modules, and this could just as well be a safety drive or some other safety device. The Siemens safety drives, and I'm sure other vendors the same way when they do ProfiSafe, we have multiple microprocessors in there. The sharing of the load and the cross-checking of each other and the checking of the safety functions, all of that is kind of the same concept as what you see here. So that's kind of how it works. And within the Siemens families, over on the right, you see we have various form factors of I/O. So some of which at the top in the IP20, the blue area, Some are mounted in cabinets, others are mounted outside of cabinets in IP65 or 67. And with Siemens, each one of those families has safety certified I/O, so that's why the little safety stamp. So whether you pick something that's small modular, or you pick something that's intrinsically safe, or you pick our higher density I/O that could be mounted remotely or right next to the CPU, or you're talking about modular I/O out in the process and an IP65 rating, or brick I/O, we have safety modules available for all of those. And so that's again where you could have a totally segmented safety system, or you can integrate right in. And so in each of these cases, the yellow is safety I/O, and the blue is standard I/O. And of course, there's various vendors that have ProfiSafe, and so whether you're using someone else's I/O, you're using encoders and all kinds of devices that are out there on safety on ProfiSafe, they would just integrate into the system. And so the left side is just a quick architecture picture of what it could look like with the purple down here. This is Profibus and Profinet, and they can talk and communicate across those. There's wireless communications going on, and you're able to communicate to safety devices or other CPUs out across the wireless. And so this is a very common approach with ProfiSafe, that you can have a very integrated solution with your standard and your safety, and integrating all the various networking. The final slide kind of on the how-to, if you had a standard system, so if we're going to add, we have an application that is just doing standard control, and we want to add safety, how would we do that? And so all of this blue, again, is meant to indicate standard functionality. So we have a standard CPU, we have standard communications going on via Profibus or Profinet, and we have our standard control program. And so what would happen is you would replace your CPU with a safety CPU. Now, you could keep separate CPUs, one CPU for standard, one for safe, but let's say you wanted to combine everything and do a fully integrated system with both safety and standard. You would replace the safety CPU and, replace the CPU with a safety CPU. You would add your safety I/O, which is where I've added some yellow modules here, and when you do that, the ProfiSafe just comes along. You don't change anything about your network, you don't change anything else about your overall structure, but by having configured safety I/O modules and safety CPU, you just get ProfiSafe. Now it will work on those networks just like your standard communications did, and then you, of course, have to write the safety logic that's going to determine what happens with those safety inputs and safety outputs. But that's really the way it goes. You just added your I/O onto your existing I/O. You did have to replace the CPU in that case, and you're ready to go. And of course, there's certifications, and there's a lot of things you have to do around that. But from a simple hardware and software standpoint, that's the approach. Now, just two quick examples. Coming here near the end here, two quick examples. One being an automotive application, and the other being material handling. And so in the automotive application, it's a robotic application. You see on the left the safety CPU, communications, and then there's the robot controller out there also communicating on Profinet. And we've actually mounted, in this case, the customer mounted safety and standard I/O right on the robot. And then they mounted I/O also on each of the tools. And so the tools, as they get plugged in, the I/O on the tool comes into play. It does a fast startup and just integrates into the system. And so in that case, again, this could be just standard control, just safe control, or both at the same time. But it's going to be high speed. It's going to allow fast startup, and it's a very robust and proven approach. On the right-hand side, pick this application of an application in a gantry, because it shows a wireless application. So in this case, the base station is here on the left, and the base station has an HMI, maybe it has a PC for more functions for the operator, an Ethernet switch, and then the safety CPU and a power supply. We could add safety and standard I/O right there, but in this case, everything is all located remotely out through this safety access, this access point, and on the other end access point, and what I meant to say a moment ago, your safety I/O is out here. There's nothing safe certified about the access points or the network itself, again, because remember that black channel aspect. In this case, the safety I/O module out here on the bridge control, it is wrapping up the safety packet, sends it through all this standard infrastructure, and then the CPU, the safety CPU on the other end, is what then evaluates, did I get the packet in the time frame? Did it get corrupted? Is it the data I need? Yes, it's all okay. All right, let's do safety control. And as well as the safe out here, you might have things like cameras and bridge control. And in this case, it just made sense to put that video on the same network. As long as you have the bandwidth again, that's fine. And so my last slide is more about design and implementation tips. And so the left side, a lot of the standards use this terminology, detecting, evaluating, and reacting. And so your safety network is going to just be part of that. And so typically ProfiSafe has a certain value for probability of failure, just like any other device does. And so when you do your calculations, whether it's for the ISO standards or IEC standards, or you're just doing perhaps EN 954 and the categories, the network is just part of the equation. And a lot of times that number is so small, vendors like Siemens might include that failure rate right in with the CPU because it really doesn't change a whole lot. But you just follow those standards. Siemens has a tool called Safety Evaluation Tool. It's a free download that will help you with some of those calculations for either the ISO standard 13849 or IEC 662. Sorry, my brain slipped there. But for the SIL levels. And then there's also Sistema you may have heard of, and Siemens has project files for doing that as well. So you can use the Sistema tool or the Siemens tool and use it right with those standards and make sure that you're validating or ensuring that you reach the safety level that you expect it to. There's other tools available out there, but just in summary and wrapping up, the ProfiSafe allows you to do things like centralized safety control, decentralized safety control, expandable safety architectures, various topologies, whether they're lines and stars and trees, or they're combined with your standard control and your video and your audio and other systems, or they're segmented. That's your choice. And from Siemens, we offer a full complement of hardware across all of our different families that know how to communicate ProfiSafe on Profibus and Profinet. And so we feel like Siemens has a very good offering around the ProfiSafe. And so that's it for me. I guess hand it over.
Alrighty. Great. Thank you very much, Tom. And now we will hear from Cory.
Thank you, Leslie. I'm going to talk to you about open safety, a little bit different concept than what you just talked about. First, what I'll do is I'll give you an introduction to open safety because many of you may not have heard of it or be familiar with it, and then we'll talk about some of the details about how it works. First, just to explain the concept, if we look at an integrated automation system, kind of some of the key pieces behind that, key benefits are high-performance field bus systems that allow you to put discrete I/O and motion on the same field bus. And some of the benefits are, easy configuration of devices, automatic configuration downloads, system-wide diagnostics. The fact that it's a single field bus makes it easier to maintain, and then, of course, taking advantage of, the higher performance field buses that are out there today. So with open safety, the concept is why not extend this to a safety solution? Here again, taking advantage of the performance of a single high-performance field bus, and then all the other benefits that come along with an integrated system, including safety now, basically allow for faster reaction times and higher performance on your safety system as well. So how does open safety fit into this? I mean, there's many safety networks out there. I think the thing that sets open safety apart is the fact that it's open and can be used on any field bus. So it's not necessarily tied, although I showed Ethernet PowerLink there, it is not tied to Ethernet PowerLink. It can be utilized on any of the field buses shown here and more. And that's the key differentiator for open safety as a safety solution. And what that means is, with open safety, you can basically pick the hardware that you want to use on your control system, the field bus that you're comfortable with using with your control system, yet still have a standard safety solution regardless of what hardware or field bus systems you select. So when you look at a line in your facility, what this means is, obviously, with any line, you get equipment from different manufacturers. Those different manufacturers may use different control systems. But the one thing that Open Safety allows you to do is standardize your safety solution, across those different pieces of equipment, regardless of the control system that they've used. So in this case, I show a blower and a filler that happen to be done with a B&R solution and PowerLink. They're exchanging Open Safety data across PowerLink, but on other parts of the machine there may be equipment from manufacturers that use different hardware vendors and different field bus systems. If Open Safety is implemented across the board, then it really doesn't matter what field bus system or what hardware is being used. That safety data can be shared across them regardless of the hardware and field bus system used. So just to kind of quickly recap what that means for Open Safety and what it is, it's a completely independent open safety protocol that's license-free technology. It's approved worldwide, and it also has a TÜV certification as a protocol, and it allows you to have a single safety solution or safety standard across your entire production line, regardless, like I said, the hardware and field bus system used. Okay, so let's start talking a little bit about how it works. I'm going to review a little bit of what Tom said about the black channel concept, because that's so critical to why Open Safety can be used on any field bus system. Basically, what's within that safety layer, which is completely independent from the communication layer, is all the mechanisms required to carry out the safety functions. So the underlying field bus system has really no bearing on the safety protocol whatsoever. Any error detection of the standard field bus system doesn't have anything to do with the safety protocol as well. It contains its own error protection schemes and detection schemes, and I'll talk a little bit about that as we move on. Now, if we look at the safety layer, you see several components, and the first one I'll talk about is the configuration manager. Basically, the configuration manager is responsible for managing everything that happens within a safety domain, and we'll take a look at those in a couple of slides, what a safety domain is. But some of the things that it does is ensure that any of the safety devices within that domain are present and operational. It'll have configurations for those safety devices that can't store their own configurations, and we'll download those when those devices are present on the network. It makes sure all the devices are unique and have their own address, and also that they have all the information that is expected of that device, whether it's vendor-specific information or parameter information. It will also make sure the devices are present on the network at all times, so it does some lifeguard checking to make sure everything's okay. The next object is the object dictionary, and this basically just establishes the format and how to access data throughout the safety system. The network management, or SNMT, basically provides the network services for the configuration manager to do what it needs to do on the network, and we'll talk a little bit about some of the communications that take place between safety devices. The service data object is basically what the configuration manager uses to do configuration, upload, download parameters. It would also be used by tools to access information on devices. So it's basically the non-processed related communications, and again, it uses the object dictionary to access that data properly. And finally is the process object, which is responsible for exchanging the process data itself, and that in field bus terminology would be like the cyclic data that's being exchanged between devices. And again, that uses the object dictionary to properly access that information. This object also contains a time synchronization service, which basically verifies network performance between any devices communicating on the safety level. Okay, so let's take a quick look at how what the communication model is that Open Safety utilizes. Basically, it utilizes a producer-consumer model, and in this case, I'm showing Safety Node 1 as the producer, and then basically any other node within that safety domain can be a consumer. Any communications that take place between the producer and consumer are identified by the producer's unique safety address. Basically, an extension to this producer-consumer model lets the producer send data separately to each consumer as well. And it really uses the same mechanisms. I think that the main difference here is the configuration manager has to assure that all the addresses of each device are unique, and also the communications now contains address information of both the sender and the receiver. And finally, some of the server-client communication that takes place, this is mostly configuration services or network management services. It just basically have a request and a response, and in this case, the configuration manager is the client, all the safety nodes are servers. Each request and each response contain the address of the sender and the receiver. And this all becomes very important when you look at systematic error detection and so forth within the safety layer. And that's what we'll look at next. So if you look at some of the systematic faults that are taken care of on the safety layer, we'll also look at the mechanisms that are used to prevent or correct those faults from occurring. So one of them is duplication of frames. And the measure that's taken to protect against that is unique timestamps. Each frame has a unique timestamp. How do we detect loss of a frame? Well, that's also using a time function. In this case, time monitoring. I think Tom mentioned this when he was talking. Each receiver is monitoring for data that it's expecting to receive, and it's monitoring to receive that data within a certain time frame. When it's outside that time frame, then corrective action needs to be taken. Another fault that needs to be handled is insertion of a frame. It could be by some other device than the sender and the receiver that are supposed to be exchanging this data. And the service that is used to take care of that is a unique identification within the safety frame. Incorrect sequence of data. Again, the unique timestamp information is used as a measure against that. Delays of frames, because again, the field bus system is totally separate than the safety layer, so there needs to be a mechanism to be able to detect delays of safety data, and that uses both time services, timestamps, time monitoring as a measure against that. Distortion of data, this could be maybe noise related. There are separately calculated CRCs. There are 2 subframes within the safety frame, and we'll look at that, and that provides some redundancy and cross-checks. And the last thing is detecting safety frames versus just standard non-safe frames. And as we'll see in just a second, the safety frame has a very unique structure that allows it to be easily identified from a non-safety frame. So taking a quick look at the safety frame and its makeup, like I said before, the safety frame is made up of 2 subframes, and this would tie directly into hardware, but because this is a little bit hardware independent, I don't want to go into details on any one specific hardware, but basically each subframe contains the same data. Up to 254 bytes of data can be in each subframe, so that means that the total payload size is 2 times that. Each frame contains address data, a unique ID, length of the data contained, time information, of course the data itself, and a CRC. Each CRC in the subframe is calculated, using the same polynomials, but will have a different signature, and is at the hardware level probably calculated by 2 different microprocessors as well. Depending on the data size, the length of the CRC polynomial changes as well. So for example, a payload that's up to 8 bytes may use a CRC 8, 1 over 8 bytes. Anything over 8 bytes would use a CRC 16. Now just a little bit about topology for open safety and how it relates to an actual machine. When you look at your machine, and maybe it's made up of several different hardware components and different field bus systems, you may want to segregate your safety system across those different pieces of hardware and field buses. So for example, Open Safety Domain 1, shown here, actually spans several different systems and a couple of different field bus systems. In this case, PowerLink and Ethernet TCP/IP. Within each safety domain, there can be up to 1,023 safety nodes. There can be up to 1,023 safety domains. Each safety domain has a configuration manager which manages all the devices, like I said before, within that domain. You can have direct communication between devices from one safety domain to the next safety domain. So if we just take an example right here, safety node 1 in this domain might be an input to an e-stop button. Safety node 2 within this domain might be a drive that uses that e-stop. Well, you have the capability of direct communication between safety node 1 in this domain and safety node 2 in this domain using something called a safety domain gateway. And the interesting thing here is this actually occurs across 2 non-safe field buses, being PowerLink and Ethernet TCP/IP. So just to recap real quickly and to talk a little bit to component manufacturers that may be interested in open safety and why should they be interested in open safety. Basically, regardless of the field bus system that hardware is being developed for, you're basically implementing one safety protocol. So that same safety protocol is used regardless of the field bus interface. A certified open safety stack is available, which makes development time much easier. It's independently managed and it has been independently certified. Although I'm not an expert in this area, I would suspect that for the individual hardware device, now that you're using a certified protocol, really all that's required at this point is conformance testing for that device. And that's a brief overview on open safety.
All righty. Thank you very much, Cory. And if anybody wants to submit, we have a couple of questions already, but feel free to go ahead and submit your questions if you have them. One of the questions that is coming in is, are there more than just these 2 types of buses for safety? In other words, do other manufacturers make safety protocol buses as well?
Yeah, absolutely. If I can answer first, there was actually one slide that named a couple of them. That's certainly not all of them. Safety bus systems are available from a number of manufacturers. I mean, you've seen really one example from Tom, but there's other ones from other vendors as well.
Okay, and here's a follow-up to that one. Do they all use the same basic protocol stack, or are there variations that make them proprietary?
And I'll take that one, and Cory, you're welcome to add once I do. What you find is there's a lot of this is based on IEC 61508, and so there are certain things that you heard common to Cory's discussion on how they implement things and how ProfiSafe does. And so you see those are kind of across the board, but the stacks themselves are generally different. You know, how things are packaged inside of the message, how large is the message, does one node kind of add on to the message from a previous node, or are all nodes sending different messages? Those kinds of things do make the protocols very different, and that has to do with efficiencies, how fast they are. You'll hear a lot of the different the people, the proponents of the different buses. They'll talk about why, this one's faster or that one's, I don't know, more reliable or whatever reasons you would give, and a lot of it has to do with exactly what the question is about those different stacks and how they've optimized it for certain kinds of applications. Cory, feel free to jump in if you like.
No, that was a pretty good description. I guess the only thing I would add is that is probably one of the key points about open safety being open is that single stack implementation that can be done on whatever hardware you want to do it on, for whatever field bus you want to do it on.
Okay, and for both of you, are there versions of these networks that operate in wireless applications?
Yes, I showed an example of one. Siemens, and I say Siemens because that's who I work for, but the ProfiSafe, the vendors that have implemented ProfiSafe have been doing wireless applications since probably 2005 or thereabouts, and really it came when ProfiSafe on ProfiNet. When that hit, it allows you to use standard technology wireless, and this may be true of other vendors as well and other networks, but yeah, there's a lot of wireless applications. The big thing with wireless is, of course, the security of the wireless in the first place, which is another huge topic, but the security of it and then the availability is the other question. If you have both of those things, then it really comes down to just response time. So wireless tends to be a little slower than say, let's say, copper. And so, if you had a hardwired network, the biggest thing about safety is the response time of the safety function. Let's say a person's hand goes through the light curtain. When that happens, then the motor needs to come to a full stop before the hand gets to the hazard. And so, if you do that wired, then you're getting basically as fast as you can go. If you did it with a wireless network, then the speeds tend to be a little slower. You may still be able to do it, but you just need to consider what those delays will be of having the wireless network. Obviously, if the network goes down or browns out, based on the things we just told you about time checks and all those other things, it's going to come to a stop as soon as that happens. But in the case of the person putting their hand through and everything working as expected, how long does it take for the whole safety function to take place?
Yeah, just to add a little bit onto that, again, from an open safety perspective, the actual media used, whether it be wireless or whatever field bus system, it really doesn't matter. All the mechanisms are there to make sure the safety function is preserved. As Tom said, with wireless, I mean, maybe the delays are longer, and you need to account for those. But everything is there that you need to do, whatever type of media that you want to.
Okay, and Tom, this question is for you. For the safety I/O that you offer, do you need an HF network adapter module?
HF network adapter. I'm not sure what that term means. I apologize. What I will say, HF network adapter.
High frequency.
Siemens has high. Yeah. You don't need anything high frequency. What I will say is there's various for Siemens hardware. There are various
high feature
head modules that we provide, and they're high. Yeah, exactly. High feature head modules are generally required, and what that means is we have some head modules that people that really want low cost, they may say, okay, all I want is discrete I/O out here, nothing special. It's just a low cost version. That's just what we call standard, and then high feature means it's one that supports things like, I don't know, communications modules and motion control modules and safety modules. So yes, the comment would be yes, you do need, with Siemens hardware, you'll, in most all cases, when you do remote I/O, you'll need the high feature head module.
Okay. And I'm just addressing somebody here. Another question, I guess Ella Bradley and Siemens, do you both support open safety now?
I'm not aware. For Siemens, I'm not aware. I mean, from the comment, I guess Cory could answer where he shows ProfiNet. I'm not sure how that works. It sounds like it will pass through. Obviously, he's saying ProfiNet. So what I kind of saw on those graphs, it looked like there was additional. What you're really doing is talking to hardware that's down in that Profi network. So it's not like a Siemens module there. No, we do not have any open safety modules that I'm aware of, and I'm not aware of any from Rockwell. Now, Cory, please jump in there.
Yeah, as far as the specific vendors go and their developments with with open safety hardware themselves. I can't speak to that. It's managed by a, open safety is managed by an independent organization, so I'm not directly in tune with all the vendors that may be working on open safety solutions. From a B&R perspective, we have done operational testing with a number of different field bus systems, including Ethernet IP, of course Profinet, Circos 3, Modbus TCP IP, and Ethernet TCP IP. And what that means is we may also be providing some hardware that can operate with those field bus systems directly. That would be some B&R safety hardware.
It's okay. I'd like to flip the question and just say that it's very common in systems that I was involved with for ProfiSafe devices to be non-Siemens that I would be interfacing or working with various other manufacturers' components on ProfiSafe, not just the Siemens component. So not really the question asked, but I guess that's the flip side of it.
Okay. Now, kind of a follow-on question, I suppose, for you, Tom, is do you need to set the safety I/O to real-time mode for the Siemens system?
Well, that's interesting. That's a detailed answer that I could go in a lot of detail, but I'll keep it fairly simple. All of the Profinet I/O runs in what's called real-time mode. So it's updating at a very fast time cycle, as opposed to the configuration data. When we send down configuration data, we allow it to travel slower, so we set it up as basically the packet is just a normal TCP/IP packet. To contrast that, when the reason I say there's a detailed answer there is the fact that somebody made this statement or asked a question about setting it to real-time mode makes me think of when we do motion applications, there's something called isochronous real-time, and that is something where, yeah, there's additional items that occur with that, and it's meant to be for things like synchronizing, I don't know, multiple drives at 1 millisecond or even much faster than that. And in that case, yeah, there is more involved. But for all of the I/O modules, all of the applications that I've ever done, they're just real time, and there's not a darn thing you do about it. That's just how they run. You put them out, you put them in, you write the program, you configure them, bang, it's done, and you're operating.
Okay,
I hope that answers the question.
Mm-hmm. Okay,
this
question is for
I just hope that answers the. I'm sorry. I hope that answers the question as it was. If they want to, my contact information's up there. If they wanted to send me an email with more details, I can get very detailed into it. But it's kind of staying at a high level. I think the answer is they're automatically in real time.
Okay, this one's for both of you. Are there any special considerations or any things that engineers need to know about when you're applying safety in process applications, as opposed to industrial automation kind of things?
I think I went first last time, Cory. You're welcome to go first, or if you want, I'll jump in first, and you can always comment. Okay. Yeah, there is, because when you talk about process applications, the standards are a little different. You're talking typically like IEC 61511, as opposed to machinery safety, which would be the one I lost earlier was 62061, or the ISO standard 13849. And so the concept there, I think a lot of response times and things like that are all still considered, but you'd end up with huge considerations on I forget the term they use, but basically the fact that you don't put all of your safety in one thing. They'll have a retention pond. It's like your last level of safety, but they'll put in a SIL 1 function, and then behind that they have like an automatic pop-off valve and all kinds of things. And that 61511 standard is very different. The concepts are the same because it's based on 61508, but it's a very different set of concerns. And so, yeah, there's a lot to consider there. I know there's some classes out there on that standard that are really, really good. ISA has one, and some others that you can take and learn about that other standard. But it's quite a different world because of the safety levels you're talking about.
Yeah, the only thing I guess I would add, I actually had an application example that is a process application. And yeah, the standards are different. I'll be honest, I'm not familiar with all the standards in the process, that relate to the process business. But the overall concept of your solution and the hardware and the safety protocols can certainly apply there as well as they were in the application example that I had.
That's a great point. I mean, a lot of the products that are out there, they're certified to both, and I'm sure, Cory's products, the ones that he's talking about, the Siemens products have both certifications. It's just, just fundamentally, machinery, when you're talking about SIL levels, they talk about probability of failures per hour, as opposed to a process application, it's probability of failure on demand, because the fundamental of a process application is it runs for very, very long periods of time and never turns off. And that means that you have a whole different type of failures to consider, because you start your car, you park your car in November, you live up north somewhere, and you go out and start it in February. Is it going to start? That's a very different kind of failure than I started every single day and now I'm having wear type failures and different things. And I think fundamentally that's kind of a difference between those two applications. The hardware and the products you use to solve that application may be exactly the same, but the things you need to consider when you do it, and of course the vendors, Siemens and others, we provide you collateral that kind of talks about those things, but it's a different set of concerns.
Okay. Cory, this one's for you. Where can an engineer get an open safety development kit?
Oh, okay. The development kit can be found on a website from IXXAT, and if there's a way that I can send a direct link out easily, let me know how to do that.
I'm not sure about that one.
Because to say it is going to be meaningless. It's got a bunch of slashes and other stuff in it.
Why don't you send that information to me at my email, and we'll see if we can include it when we send out the presentation. Just as a reminder to everyone who has registered will be receiving the URL address to this presentation in the next day or so. And the people who asked about the process information, we're very glad of that answer. They said it helped them a great deal.
Excellent. Good. Thanks. And if any more questions, shoot me an email, or obviously you can go through Leslie and ask questions, and she can go to me if you want to remain anonymous, and that's fine.
You will be contacted.
Perfect. That's fine.
Okay, we do have a couple more minutes if anyone wants to submit additional questions and have them asked online on this webinar. Otherwise, you see both Cory's and Tom's email addresses on the screen as well as their phone numbers. So feel free to contact them either way for additional information or for something more specific to your application. And I'd like to thank you both for the presentation. It was an excellent presentation, and I think it addressed a lot of issues, as safety is becoming something that is important in nearly every design.
Excellent. Well, I appreciate the opportunity.
Yeah, thank you, Leslie.
Okay. Well, there do not seem to be any more questions coming in at the moment, so just be aware that this information is on your screen. And we will be sending out the presentation to you in the next day or two. So I'd like to thank everyone for attending, and thank you again, Tom and Cory.
Okay, thank you.
You're welcome. Thanks.
Thanks. Bye-bye.
All right, goodbye.